Hello and welcome again to my physics online video lecture series. In today's video, I'm going to be discussing RC circuits. Specifically, we want to look at the equations side of RC circuits. I've got a separate video in which I dig into the graphs quite a bit. This one is the equations video. We're going to be looking at this from an introductory physics of calculus perspective. We can begin by recalling that when we have a complicated looking circuit, we might be able to solve it using the Kirchhoff's rules. This includes the Kirchhoff voltage law, KVL, and the Kirchhoff current law, KCL, sometimes also called loop rule and junction rule. And so that's kind of the big part right there. Second item is that the voltage drop across a resistor is given by current times resistance. For a capacitor, the voltage drop is given by the charge divided by the capacitance. And for a battery, we can just use the battery EMF unless we want to include some internal resistance. So basically delta V will look like EMF minus the internal resistance times the current, but for our purposes here we're going to take the internal resistance to be small. So with that, we're basically ready to analyze a circuit, specifically one which contains a resistor and a capacitor. So here's the basic diagram of what we're trying to analyze. We have a DC power supply such as a battery, which we're going to label as having a output of EMF. We have a resistor R, we have a capacitor C, and I've put in here a switch that can be either moved to this position. So this position is charging, so the capacitor will be charging up. This one right here is discharging. So if the switch is moved down to this position, the capacitor will actually be discharging. And so this is the basis for, or these right here are the basis for our analysis of this circuit. So I'm going to actually call these positions 1 and 0. So these will be positions 1 and 0. So we specifically are interested in the loop rule, so Kirchhoff voltage law. So if we close the switch to position 0 so that the capacitor is discharging, the Kirchhoff voltage law for that loop basically will have a delta VC plus a delta VR equals 0. And so what you end up getting is Q over C plus I times R is 0. Now, another thing that we might add to the recall is the relationship between charge and current. So current is rate movement of charge. Thus, we can write that I is defined as dq by dt. So this equation becomes Q over C plus R times dq by dt equals 0. And so if we isolate dq by dt on one side of the equation, what we have on the other is 1 over R times C times Q. And so this is basically a differential equation, and we'll solve it sort of shortly. So I'm just going to kind of like partially box this in and note that this is the discharging case. Now the charging case if I were to apply that same loop rule, what I will now have is the voltage drop due to the power supply or battery plus the voltage drop from the capacitor plus the voltage drop from the resistor is 0. And so substituting and keeping track of signs, basically I will have the EMF minus Q over C minus I times R is equal to 0, and thus I have dq by dt is equal to 1 over R times epsilon minus Q over C. And so this is a different differential equation. You could also write it as epsilon over R minus 1 over RC times Q. But this is a different but similar differential equation, and it describes the charging case. So now the question is, what are the solutions to these differential equations? A little bit of math that maybe goes beyond the usual scope of a Physics 2 course, in the sense that, again, I understand most of you taking this course are taking maybe Cal 2 or at most Cal 3. A handful of you might be taking differential equations or a math methods course, but most often that's not the case, and in fact most places this course would be the prerequisite to your math methods course for physics or physics and engineering. And in that course usually these differential equations are covered and how to solve them. So what we'll do here is note that we're looking in equation 0, this one, for a function of time, q of t, such that when I take the derivative of the function, I get back the function multiplied by a negative 1 over some constants. So basically what I'm expecting is q should be charge as a function of time such that dq by dt is equal to negative q over some constant. And we'll represent that as negative q over tau. The solution to that equation, one approach is to just guess at a solution and then see, does the solution work out? So you could take a few guesses. What you'll find is that the solution that works out for this is that q of t needs to be some maximum value of q times e to the negative t over tau, where this tau was this constant. I pulled it out of this equation in the first place, so tau is equal to RC. Tau equals RC, and if you were to divide everything here by capacitance, what you would end up getting is V of t is equal to some maximum voltage e to the negative t over tau. And so that is the discharging sort of equation. And in fact, I say maximum, really a better answer here is initial. So this is for a discharging, this is position 0 discharging. For the other one, what you have is an inhomogeneous solution. And the way that you basically solve these is, first of all, you kind of solve for the inhomogeneous part. In other words, suppose Q is constant, right? Well, if that's the case, then dq dt will be 0, and so that constant value of Q has to satisfy essentially that 1 over R times epsilon minus Q over C must be 0. And so what that implies is that you have some Q value, so Q naught, which in this case actually will be the maximum value. Q max should look like epsilon over R. And also solve the homogeneous version. So we've got the inhomogeneous or non-homogeneous, we got the homogeneous version of this equation. The homogeneous version is actually just this first equation that we solved. And so what this basically does for you is it lets you sort of solve the differential equation in such a way that you end up with Q of t is equal to, and then it's basically Q max times 1 minus e to the negative t, again over tau. Again, tau is RC. And therefore V of t is equal to V max, which in this case is your epsilon, times 1 minus e to the negative t over tau. And so that's what gets you your two values. I messed up on my notation here though. This should be an epsilon over C. Charge is voltage, or excuse me, voltage is charge over C, and so this charge should actually just be epsilon C for the maximum charge. Alright, so that kind of settles the math of these two. And there's a few little things to point out. One of them is that in both cases tau is equal to RC. This is what's called the decay time constant. And the decay time constant is basically the time that it will take for these gravs to decay by a factor of 1 over the natural number e. And I'll talk a little bit more about that in another video in which I show some actual plots of these voltage versus time and so on. Now this decay time constant, tau equals RC, is actually related to another quantity of interest to us, which is what's called the decay half-life, which we might write as t1 half, is actually equal to this decay time constant times the natural log of 2. That also means that if you want to solve for the decay time, you can take the half-life and divide it by natural log of 2. In any case, this half-life is basically the time for the charge on the capacitor, or the voltage across the resistor, let's say, or the current through the resistor, whatever, to decay to half of its maximum, that is, its initial value. We can actually extend this further by picking other values. As a general rule, if you want to define a t1 over x, then that should be tau times the natural log of x, where t1 over x is the time for the voltage or the charge on the capacitor, or the voltage across the resistor, or the current through the resistor, or whatever, to decay to 1 over x of its maximum value. So if you want to know what is the quarter life of the circuit, take tau, that is RC, and multiply it by the natural log of a fourth. So let's conclude by doing a set of examples, or an example of several parts to it. So suppose you have a certain RC circuit with a known capacitance and resistance, and it's discharging from an initial voltage of 24 volts. That's across the capacitor. What we want to determine is the decay time constant, the time that elapses until the voltage across the capacitor is 12 volts and also 6 volts. This right here is, of course, at time 0. And then also figure out what the current is through the resistor at time 8 seconds. Okay, so to solve those, we'll just kind of go in turn. The decay time constant is tau. Tau is R times C. So that's 0.25 millifarads times 20 kilo ohms. Now milli and kilo are sort of opposite prefixes, so they kind of cancel. And so what's left is 0.25 times 20 farad times ohm. Farad times ohm is seconds. So 20 times 2 times the 0.25 is 5.0 seconds. So that's your decay time constant. B, we want to know the time until the voltage across the capacitor is 12 volts. Now there's two ways of doing this. There's the just use the equation way. Basically you have V is equal to V naught e to the negative t over tau. What this implies is that V over V naught is equal to e to the negative t over tau, and hence that negative t over tau is the natural log of V over V naught. To get rid of exponents, you take natural log, so we take the natural log of both sides. And then basically you can plug in or solve for everything. So this would be basically just t is equal to negative tau ln V over V naught. For what that's worth, that is equal to tau times natural log V naught over V. And so we use that 5.0 seconds that we found on the previous times the natural log of V naught over V, which was 24 volts over 12 volts, or in other words 5.0 seconds natural log of 2. There's a shortcut to all this though, if you're a little bit more intuitive, and the shortcut is this. Okay, this gives me a time t of 3.47, so let's just call that 3.5 seconds. The shortcut is to come back over here and realize that this time right here, 12 volts, is half of my initial 24 volts. So this is 1/2 initial. So we're looking for the half-life of this problem. Thus, we could have sort of skipped all of this reasoning here and all of this reasoning here, and simply looked at this, realized that we needed a half-life, and come over here and just done tau times natural log of 2. And that gets us the same answer. In fact, we have tau natural log of 2 right here as the last line. So by similar notes, this right here was the time to get to 12 volts. The other one that we're looking for is 6 volts. And so that 6 volts value, switch colors here, 6 volts value, this is 1/4 of 24 volts, excuse me. So this is a quarter time. And so that should be 5.0 seconds times the natural log of 4. And so, that actually should be double the previous answer. So what we get is about 6.93. The other one was 3.465. Here we are, 6.93. So you could have like a little 3 here, seconds. This one was 3.4657 ... seconds. This 6.9314 ... seconds. All right. Either way, we've solved part B. We're ready to tackle part C. We want to know what the current is through the resistor at time 8 seconds. So at t equals 8.0 seconds, what we would have is that V for the capacitor is equal to V naught e to the negative t, which is 8.0 seconds. We'll just write in a t, divided by tau. So this is 24 volts e to the negative 8.0 seconds divided by 5.0 seconds. So we got to plug all that into our calculator. We have 24 times the exponent to the negative power of 8 divided by 5. And what that gives us is about 4.845. So we'll just call that 4.85 volts. And now what we need to use is, again, the Kirchhoff voltage rule. So if we come back up to this voltage rule, we're basically looking at this particular part of the circuit. And so if I was going to draw a diagram for this, I basically have something like this, and then they're connected here. And so VC and VR must be equal to each other. Therefore, delta VR is also 4.85 volts, and you know that delta VR is I times R, so I must be delta VR over R. So the current in this case is 4.85 volts divided by the resistance. Going back up here, what was our resistance? Our resistance was this, our capacitance was this, our resistance is 20 kilo. So we have 20 kilo ohms. And so if I divide this number that I just got by 20, what I get is 0.242. So let's call that 0.24. And the units, I have volts over kilo ohms. That gives me milliamps. So that is my current at this time, 8 seconds. All right, so that was, I hope, a nice set of examples for all of you. Hopefully you find that that's enough examples for one short video. I really hope you learned something from them. And as always, thanks for watching.